Here we go. Chapter 3, Section 3, Radio Astronomy and Interferometry. I have to say my own interest in radio astronomy has grown greatly since my trip to Chile, and I'll be talking a little bit about that in just a minute. Radio telescopes really began in about the 1950s, maybe a little earlier than that. Grote Reber from Illinois and Karl Jansky were some of the pioneers who first started listening for radio signals from space, if you want to call it listening. Radio, remember, is an electromagnetic wave. It's a form of light. You could call it radio light. And for 400 years, or 350 years or so, people had only looked for visible light, the stuff that we see with our eyes. And we were leaving, that's really just a thin little sliver of the whole spectrum of quote-unquote light that's out there. And nowadays, of course, we look at everything. We'll get to that later. But radio waves are of particular importance for a lot of reasons that we'll get to in just a minute. Now, what does a radio dish look like? Well, here you have one on the side of your house, perhaps. A direct TV dish is a perfect example of what a dish does. You have a curved area here as your main dish, and it's curved in a parabolic shape so that incoming radio waves all bounce off in the same direction. They all focus at a point called the focal point or the focus, and that's where you're going to have your instrumentation. That's how they all work. So they all go to that focal point or prime focus, whether it's a direct TV dish on your house or one of these mammoth telescopes we're getting ready to see. Speaking of which, let's take a look here at some of these dishes. You know, why are they so absolutely incredibly huge? Well, for one, they have to be. You're talking about incredibly weak signals from space. The kind of things that astronomers are going to need to study with radio signals are very weak. And so just like, and again, we don't want to, maybe that's a bad example. I was going to say, you know, to hear something, the larger ear you have, the better you can hear, you know, a sound, the fainter sound you can pick up. But really, it's more like your eyes. The bigger eyes that you have, the more light you can collect. But here's the good news. You have to make these dishes huge. And one more reason, I'm sorry. Not only are the signals from space faint, but also there's a problem called diffraction, where waves naturally will spread out. It's why you can hear somebody in another room. If I'm speaking loudly, sound diffracts and it spreads out through a room and you can hear me around a corner. Turns out the longer the wavelength is, in this case with electromagnetic waves, with radio, the more it's going to diffract. That's a problem because you're trying to focus radio. You don't want it to spread out. The solution to that is to build, guess what? Really large dishes. So for two reasons, you have to build large dishes, but the really great news is it's actually easy to make large dishes, at least relatively easy compared to, let's say, making large mirrors for visible light. For one, they don't have to be smooth. They spend months. When I visited the mirror lab in Arizona, they will literally have machines spend months polishing those mirrors because they have to be right. They have to be smooth to the nanometer scale because that's the wavelength of visible light. Radio waves are big. They can be, the size of this room that I'm in. And so you can have actually like large gaps and so forth in a radio dish, and to a radio wave, that just acts like a solid surface. So anyway, it doesn't have to be smooth, so they don't have to make it, it doesn't have to spend that time trying to smooth it out. So it's relatively easy to make them large. They don't have to be as exact. And we've made some large ones. The largest for a long, long time. This held the record for about 40, maybe 50 years. The Arecibo dish, 305 meter wide dish in Puerto Rico. I've been to Puerto Rico. I actually haven't been to the dish, I must say. I have to get there sometime. Here it is. Look at that. Built right into the hillside there, right into that valley. Pretty amazing. But look at it. I mean, it is, again, no different than a direct TV dish because you have this curved parabolic surface. Radio waves come in from space and they bounce right up to the focal point there where you have your instrumentation to record that. This was, by the way, in some movies. I think most notably a James Bond movie where it was, I think, filled with water. It was a lake. It was like the hidden evil lair or something like that. Look at this. If you want to get some scale here, look at this. This is the walkway. Look at that. Look at the people there walking out to where that equipment is at the focal point. And for the record, you look at it, here from up high, from a high altitude, it looks solid. But right down there at the bottom right, you see that's what it actually looks like. So unlike in the James Bond movie where it's filled with water, you couldn't, you don't want it to fill with water, obviously. You want the water to come through. But remember, those long wavelength radio waves, they can't get through those little slots there. So it's going to act like a solid surface. That way you don't have to make it solid. You can save on weight, save on materials and cost. Well, anyway, the Chinese, look at this. They blew that one out of the water. So that held the record for 50 years or so, 305 meters. And the Chinese just announced that they'd finished one here called FAST, 500 meter aperture spherical telescope, FAST, 500 meters. So that's a monster. That's now obviously by far the largest single dish in the world. But both of those have one major disadvantage. You can't turn them. Just whatever is kind of overhead is what you get to see. For a movable radio dish, I don't know if this one's still the largest. I think it is. In Green Bank, West Virginia. That's the home of the NRAO, the National Radio Astronomy Observatory. There are all kinds of these dishes scattered throughout the hillsides. It's a beautiful area. And I hope to make it up there sometime in the next couple of years and check out the facilities there. Anyway, why is radio astronomy important? Well, one advantage is you can do radio during the daytime. The sun blocks out with so much visible light, it's overpowering. But the sun is not overpowering in radio. So you can do radio day and night and still get signals. Radio waves cut through clouds and weather and stuff like that. So unlike visible light, where all it takes are some clouds to ruin your observing, not so with radio. So that's pretty neat. And, most importantly is this. I mean, you have certain things in space that you have to use radio for. Either, as you see in number 3 here, there are things that just are strong radio sources, things like pulsars. That'd be a good example for you to write down. A pulsar there is something that's going to not be strong in visible light, but would be strong in radio. So it's exactly the kind of celestial object radio astronomers would study. And what's really great about it is, just like it can go through clouds in our atmosphere, it can also go through clouds of dust and gas in space. So it can go into areas that otherwise we'd have no chance of looking at. Places like the center of our own galaxy. It's one of the hardest places we have to study in space. And that's when you would use radio waves for that. So that's just pretty awesome. Anyway, radio astronomy was the first place where interferometry was used. And interferometry is combining multiple dishes or mirrors, whatever you're working with, antennas. If you can combine them in multiple ways, that's an interferometer, which is a very powerful thing. The first time it was really done on a big scale was with the VLA, the Very Large Array in New Mexico. I'll show you a picture of that. 27 radio dishes all connected. There's the Allen Telescope Array in California. Alma, that's my new favorite right there. The Atacama Large Millimeter Array, Submillimeter Array in Chile. 66 dishes. And on the drawing board is the Square Kilometer Array. So that picture there does not exist actually yet. That's what they're hoping to build. So again, all of these act kind of like a compound eye. If you look at an insect's eye, they're all working together to give you that single image. And it is not easy to do. But it's a lot easier to do with radio than it is with, let's say, visible light, for example. So we'll start here and look at some radio arrays. There's the Allen Telescope Array, just some kind of small dishes there out in California. There's one single dish of the big VLA in New Mexico. It has that kind of Y shape. It was seen in the movie Contact. That's where Jodie Foster first gets the signal from space in that classic movie. But for now, I want to head to northern Chile. So this little give you perspective here on where we were on our trip. This is the high site at Alma that I'm zooming in on now. That's where the staff works on the high site and where the computer is. And just a little ways away there, you get to the central cluster of dishes. Now you're only seeing 8 of them here out of 66, but that's because they're spread out over miles. So we only got to see really a fraction of them while we were there. That's the road to Alma, way out in the Atacama Desert. That's a volcano there. Dr. Stephen Case, great guy there. I just happened to capture that picture of him photographing the sunset. That was one of my favorites. Oh, they have these guard animals there. That's at the low side at Alma. That's before you go on top of the mountain. And this is the control room. That's a European researcher there studying black holes. That gives you an idea of what a control room looks like for a world-class observatory. Guess what? Just like everything else, it's all about the computers. And that's where they're doing the research down at the lower altitude site. That's Dr. Tim Spuck. I'm going to keep on going here, but he is works for the government agency called AUI that manages a lot of these sites, such as Alma. And there it is. That's at the high site, that central cluster of dishes. This was an amazing trip for us, an amazing opportunity to go up there. Most tourists don't get to go to this high site. I mean, it's like being on Mars. You have the high ultraviolet and the low oxygen and super frigid and so forth. But on top there at the high side, look at this. You have a supercomputer. And I'm going to talk here for just a moment about what that supercomputer does. Okay, right here, this is the highest altitude supercomputer on Earth. And this takes, now for you math teachers, this is pretty neat. You have 66 antenna that are operating the microwave part of the spectrum. The 60 is what counts in astronomy is the baseline. It's the distance between the dishes. Well, 66 dishes end up forming 1,260 baseline pairs. All of those signals have to be processed by the supercomputer using a fast Fourier transform, which you can imagine is incredibly difficult to do. And that's what this computer does right here, and it makes it all into one single waveform. All right, so that is just unbelievable. You have this web of connections of all these dishes, and it has to be managed. It has to be put into a single form, just like I said, kind of like a compound eye. It's incredible. So here I am checking out there. That was our first moment there of going out and seeing the Alma dishes, which was amazing. I do a little report from outside. There we are, stuck in the snow at one point. And this was in June, which was kind of weird, leaving summertime here in Florida and going down to wintertime and just getting into winter in northern Chile. But here's the kind of thing they can do at Alma. They're really proud of this image, and rightly so. That is a newborn star and the disk of material swirling around it. And then look at that, what they've seen here through radio, which again is the perfect place to kind of penetrate these dusty areas. They see these tracks. You see kind of these spirals there. Well, guess what they think those probably are? Those are planets. Those are baby, like planetesimals. They're not even real planets yet, but they're scooping up material and they're carving out their own little groove. And someday they will be full-fledged planets. Maybe someday they'll have life. We're watching the birth of a solar system right there, folks. So there are a couple more pictures of Alma. It's just amazing. This is the VLBI, the Very Long Baseline Interferometer. We have ones around the world that can combine. You see some of the ones there, Green Bank and so forth, that I showed you in this video today, that they can all combine. So here, yeah, we'll take one quick look. Actually, yeah, you can see there at the bottom some Alma and some of the larger arrays now. So Alma currently is the largest one at 66. There's FAST from China now as the largest single radio dish. That's the cutting edge of radio astronomy. It's really fascinating stuff, but that's where we're at in astronomy, looking at places like the formation of planetary systems and so forth, and studying the center of our own galaxy, places that can only be done with radio, and it's made much better by interferometry, by combining multiple dishes. Thanks for listening.